a little bit about 2 by 2 linear systems. Should be mainly review, but I wanted people to be up on this. So that means 2 equations. 2 by 2 means 2 equations in 2 variables. So for example, we could have x plus 2y equals 3 and x minus 3y equals, oops, that's supposed to be y, equals 4. Well, we talked about a little bit about solving these things. We're going to do a lot of solving for bigger systems. Substitution and elimination are the 2 main strategies here. But I wanted to talk about some of the graphical interpretation stuff and some of the weird things that can happen. So for this, let's just go ahead and let's see if it'll actually plot the whole thing. No, too many rows. Okay. Let's just plot this line. And then let's plot this line as well. So we'll go in here, we'll add an item and Control V. So now it's going to plot these 2 lines, and the intersection, of course, is where it's the one pair of x and y that satisfies both of these equations. And so graphically, any line, any linear equation in 2 variables is going to be a line in the plane, and the solution to a system is going to be the intersection of those 2 lines. So usually there's going to be one and only point where those 2 lines intersect. But of course, it's not hard to guess that there's going to be some other special situations. So for example, if I had x plus 2y equals 3 and x plus 2y equals 4, then let's see what happens there. Let's modify that second equation and see what happens. Now we've got lines. For example, if I solve for the slope of this line, I could solve this to make it y equals 1/2 times 3 minus x. And so that's going to have, let's write it out. That's going to be minus 1/2 x plus 3/2. Well, this one is going to turn into y equals 1/2 times 4 minus x. So this can have the same slope, but a different intercept. And so they're going to be parallel. And so no intersection. And that means there's no solution. So that's something you have to be prepared for, that you might get that there's no solution. And there's very simple geometric reason that those lines might be parallel. Even a little more subtle would be, suppose this is 3x plus 6y equals 12. Now the left-hand sides aren't identical, but the left-hand side of the second equation is a multiple of the left-hand side of the first equation. And it's obtained by multiplying this by 3. If I multiply this by 3, I don't get 12. And so those are again parallel lines. Of course, I just multiplied this by this whole thing by the same number, 3. So that's exactly the same line. It has exactly the same mx plus b form. It's exactly the same geometry. It's just a little bit more disguised. So anytime this left-hand side is a multiple of this left-hand side, you're going to wonder they're going to be parallel. Or what if this were a 9? And so this would be a 3 if you solve it. Let's see. So this would actually be, let's resolve it. It'd be 1/6 times 9 minus x. But that's still minus 9 minus 3x. That's still minus 1/2 x plus 3/2. Now it's exactly the same equation. It's just this first equation multiplied by 3. So if I do that, I'm not going to get 2 lines here. I'm just going to get the 1 line. If this is 3x plus 6y equals 9, let's see if the computer's smart enough to realize that those are just the same line. It's probably going to be pretty slow because it's not going to realize it. It plotted them both most likely. But I just get the 1 line. Okay. So one possibility was parallel, but the other possibility is they could be the same line. And so we're going to get many, many solutions. We're going to get an infinite number of solutions. But one really important thing is we want to go beyond that. We want to actually say what the solutions are. If I just say there's an infinite number of solutions, that doesn't say that much. If I say, okay, is 7, 6 a solution? If you just know this answer, infinite number of solutions, you don't know the answer to that. Or if I want you to create 5 solutions to this equation, you can say, there's an infinite number of them, but I can't actually come up with a single one. That's not good. Okay, so we need a way to create the solutions systematically. And this is going to be especially important when we get to a 3x3 system or bigger. And so all that we have to do is basically, in 2x2, if these are the same equation, they contain exactly the same information, so I don't really need to use both of them. And then what I've done here is a perfectly good way to make it very, very explicit. Because here, I can put in any x I could possibly imagine, and then the corresponding y is going to be a y value. So the way we write this as the solution set is all pairs x and minus 1/2 x plus 3/2. We just go ahead and solve for one of the variables in terms of the other. Here it's usually y in terms of x, but there's no incredible need for that. Just solve for one variable in terms of the other, and then just say it's all of these where x is any real number. That's an extremely explicit way of describing what the solutions are. It's explicit in the sense that it's a great way of generating them. I just pick any real number and put that in the first component. I calculate this, that's the corresponding y value on this line down here on the picture, and then that's going to be a pair that's going to be a solution. So that's something you're going to need to be able to do, is that when there's an infinite number, you don't just say, oh, it's the same line infinite number. We actually want to write it out in this way. And the book has examples of that as well, which you should look at.